Yeah, so I submitted 2 models for the Motility task and 1 model for the Morphology task. And I, of course, use convolutional neural networks, both 2D convolutions and 3D convolutions based on the task. My convolutional networks are pretty simple, so our goal is pretty much to get a baseline performance for naive approaches for this task. So some challenges in this task is that we only have a small amount of videos, like 85 videos. So constructing large networks and training them is a pretty hard problem. Also, even though they are videos, so videos have a lot of frames, you can probably train over the frames, and then maybe you have a lot of data anyway, because you can have all these different frames. But because of the nature of the task, it's probably best to assume that the sperm cells have a pretty homogeneous distribution throughout the frames, so that we can increase the data size, the number of points to train on, instead of having very different sperm cells and then having to train over the whole video and predicting over the whole video to get an accurate score. Assuming the data is homogeneous, we can do some data augmentation, primarily cropping the video. So we used small sections of the video and then randomly choose small sections of the video, and also do some noise injection and flips. So for the motility, I trained 2 models. The first one is a very simple model, only 3 networks doing something important. So this is if there's something really obvious, just trying to look at the gray, the sum of the grayscale values, and this can maybe correlate to concentration of the sperm cells, and this can again correlate to the distribution of the classes. And of course, and I'll also train a more complex model, not that complex, but a bit more substantial than the first one, to actually have some chance of getting decent scores if the if the features aren't that obvious. So for this task, motility, we assume that temporal information is essential. So we sacrifice some of the resolution of the videos to increase the number of frames that our models can digest. So in this task, it's natural to use 3D convolutional layers to preserve both temporal and spatial information. In morphology, however, temporal information may not be that important at all. So we try to preserve the resolution of the image instead. So yeah, our network isn't that deep here either, and it's similar to the more complex network from the previous for the motility. Yeah, and it's still pretty simple. To avoid having the network too deep, because in other related experiments I found that increasing the depth just by naively increasing the depth made the network lose every bit of information throughout the network. So to avoid having a much deeper network than this, I use large kernels and large strides to shrink the image as fast as possible. And also, we don't want too many, when we flatten the network before going over to dense, we don't want that high dimension vector to decrease the number of parameters to train. Yeah, so of course, it's natural to think that when looking at the effects on individual sperm cells, it's important to have high-resolution images for seeing small features of the individual cells. Yeah, so in training, as I mentioned, we do some data augmentation. So for each video, we retrieve 20 augmented samples, where the samples are cropped and flipped and use noise injection. So, and also we do some, we interrupt the training after 15 epochs if the model didn't improve in the validation split. And the validation split is not the validation split I'm describing later. It's with noise injection and data augmentation for like, so we only have to take 20 augments instead of all the augments a video will generate. Yeah, but when we finally validate the networks, we still want to keep the same dimension of the inputs, so we crop the videos in the upper left corner. If it's well, for morphology, we don't really crop the videos at all because we preserve the resolution. But in motility, we crop the videos to the same size, 128 by 128, so the networks can. So what the networks train is valid for the final results. Yeah, and to train on the whole video, we split the video up into 15 frame blocks, and then for our final score, first we take the mean score for each video individually on all blocks, and then we take the mean of those scores as a final score. So our results for motility. Clearly, the simple model is unable to learn anything, especially in the third fold. It gets really horrible scores for some reason. While the complex model is actually able to get very decent scores, I think. A lot better than the 0R. And this illustrates that, of course, the features aren't that obvious as I described earlier. But they're still able to be perceived by a relatively complex model. For morphology, even though it was a lot shallower than I tried earlier, it still didn't manage to beat the 0R score. So yeah. It didn't really perceive any useful information from the videos. So we managed to achieve some reasonable scores using motility, using convolutional networks to predict motility. However, predicting morphology seems like a much harder problem, not really solvable by, well, solvable, but like throwing a neural network directly at it doesn't seem to produce any decent results. So maybe for future work, it would be very beneficial to generate models that are more specific to the task instead of general convolutional networks. So probably doing some pre-processing in tracking individual sperm cells would be useful for the morphology, at least, to look at individual sperm cells that are interesting. And for motility, you could probably benefit from also visualizing each and marking each individual sperm cell for easier. Yeah. So, any questions?